In this video, we'll calculate the pH of a strong acid. Hydrochloric acid is a strong acid. I might recognize that it starts with hydrogen, and that's usually the sign of an acid. And by saying that it is a strong acid, we mean that it dissociates completely. So that if I have HCl and I want to write its dissociation equation, it completely splits to form hydrogen ions and chlorine ions. And this would happen 100%. So that I will not have any neutral HCl molecules in the solution. They will all split or dissociate to form hydrogen ions and chlorine ions. Now, why do we care? Well, eventually, if I want to calculate the pH of a solution, pH is calculated as opposite log of the hydrogen concentration, which we could also write as that H3O plus 1 hydronium. Numerically, it's the same value, regardless of whether the hydrogen is by itself or whether the hydrogen has attracted itself to a water molecule. It's the same concentration of hydrogen or hydronium. Well, here's why I care that the acid is strong. They tell me in part A that I have a 0.001 molar HCl solution. So really that would have meant that somebody took 0.001 moles of HCl and threw it in a liter of water, or enough water to make a liter of solution. And so really then it's like saying this was 0.001 moles per liter, or big capital M for molarity. But technically, to find pH, I want opposite log of the hydrogen concentration. I want this guy right here. I want to know how much hydrogen will be in the solution. By knowing that it's strong and that it dissociates completely, I will get 0.001 moles of hydrogen and 0.001 moles of chlorine. It dissociates fully. Strong acid. Well, in the end, I don't really care so much about the chlorine. It's there. It's fine. It's not hurting anybody. But to calculate pH, I need this guy. I need opposite log of the hydrogen concentration. And the nice thing about a strong acid is that since it dissociates fully, the concentration of hydrogen will be the same as the concentration of the original acid. So in a sense, these become kind of no-brainers, that this is just going to be opposite log. I'll plug that in, opposite log of the 0.001 molar hydrogen ion. It's the same as the concentration of the original acid because it dissociates fully. And you may or may not be super familiar or comfortable with logs. They'll always be log base 10, and you can just plug it in your calculator. You just hit opposite, then the log key, 0.001. And you should get a big fat, there we go, 3. pH is 3, which I guess makes sense. It's an acid. The pH should be something less than 7. Now, again, here's why it's important that these are strong acids, because we need the amount of hydrogen in the solution. And if I know the original concentration of the acid, that is the concentration of the hydrogen ion. We cannot do that with a weak acid. If I had a 0.001 molar weak acid and it does not fully dissociate, then how do I know the exact amount of hydrogen produced? It would be something way less than 0.001. I would need to know the exact percent of the original acid that dissociates. Is it 1%, 2%, 3%? I don't know. I would need to know that, though, in order to calculate the pH of a weak acid. So I could figure out, well, how much of the original does split? How much hydrogen is really formed in the solution? And that is something that we'll save for a second year course. In the first year course, we stick to the strong acids. So the amount of hydrogen is the same as the concentration of the original acid. And so these become kind of no-brainers, right? And again, the more familiar you are with logs, you might also recognize this, that if you took this concentration and put it in scientific notation, it would be like 1 times 10 to the negative third. I would put my decimal spot backwards. 1, 2, 3. Oh. Well, remember how we said that the log is the exponent of 10 and pH is the opposite log. So it's the opposite exponent of 10. So if you look at these concentrations in scientific notation, if it's a 1 out in front, then the pH just is the opposite exponent of 10. Now, if you're not familiar with that, you just plug it in your calculator. The only time that you can't just say, oh, the pH is the opposite exponent of 10, is something like B, where we don't have a 1 out in front. That 2.5 is kind of funky. Now, I can still estimate that the pH is going to be somewhere around a 6. But this one I really do need to plug into my calculator. And so I've got this HCl solution. pH will just be opposite log of the molarity. 2.50 times 10 to the, whoa, that's a funky looking 10. I can do better. 10 to the negative 6. And that would be the amount of hydrogen in the solution. A strong acid would dissociate fully. So you just plug it in. Opposite log 2.50 times 10 to the negative 6. And I would highly suggest at some point trying this on your calculator to make sure that you are entering it correctly. You should be getting about a 5.6. I'll leave 5.60 maybe. And there she is. Now here are some interesting things that come out of this. Number one, if these are acids, the pH should be less than 7. If this were an acid and you plug something in your calculator and you got a pH of 12, that's not quite right. Or if your pH was like 36, that's really not right. And obviously we're looking at a pH scale between like 1 and 14, but this really should be something less than 7. Number two, it's close to 6. I mean, if I just went opposite exponent of 10, the pH should be 6. If this were multiple choice and my calculator died, I would be looking for something close to 6. But if you don't have a 1 out in front of your scientific notation, just FYI, your pH will end up being a decimal. And that's totally fine. pH values don't have to be whole numbers. We can have decimal or fractions of a pH unit. But it should be close to the opposite exponent of 10. Here's the other thing that we should mention. It drives me bonkers when people will say that like a strong acid has to have a pH of 1, 2, 3, and a weak acid has a pH of 4, 5, 6, or whatever. Because look at this. It's hydrochloric acid, and hydrochloric acid is a strong acid for life. It's always a strong acid. What makes it a strong acid is this. The fact that it dissociates 100%. That's what makes it a strong acid. But now check this out. I have a strong acid with a pH of 5.6. And now you might be freaking out because you say, well, but my teacher said that strong acids have to have a pH of 1, 2, 3. Not necessarily. pH is a measure of how much hydrogen is in the solution. Look at this molarity. This molarity is really small. In fact, there's no way I could make a concentration like that in our lab. I can't measure out 2.5 times 10 to the negative 6 moles in a liter of solution. That number is crazy tiny. Now, in more sophisticated labs, that type of a solution can be created. I mean, I just don't have the electronic balances that can measure out to that many teeny tiny decimal spots. We would say that this solution is dilute. Dilute means a low concentration. Low concentration. It's very dilute. Well, that just means that there's not a lot of HCl per liter of solution. Well, if there's not a lot of HCl, even though it dissociates completely, there's just not going to be a lot of hydrogen ion produced. I'm not starting with a lot of HCl molecules. That's crazy tiny. And so it's possible that you can have a strong acid with a pH of like 4, 5, 6. But then it must mean that it's very dilute. It means that the concentration of that strong acid is super small, so that even though it's strong and dissociates completely, I'm just not getting a lot of hydrogen produced. On the flip side, you could have a weak acid with a pH of 1, 2, 3. It would just mean that the weak acid has to have a really high concentration. It must be a highly concentrated solution because a weak acid would not dissociate fully. But if it was really, really, really concentrated and there were a lot of moles, well, then even though it doesn't dissociate fully, I could still get a pretty good amount of hydrogen in the solution because the concentration was so high. So anyways, I'll stop rambling. But it's like something that drives me bonkers, that it's okay to have a strong acid with a pH of 4, 5, 6. In a nutshell, then, it dissociates completely, but it means that the solution was very dilute.